Let's take a few minutes to discuss hydrohalogenation. As you learned from the text, alkenes are good nucleophiles. They are a source of electrons here with the pi bond, and we can use a hydrogen halide, in this case HBr, hydrobromic acid, to protonate the alkene and form it into a cation. So we can draw the mechanism. This is a proton transfer step. As every proton transfer step is, we should use two arrows. And as we read about in the textbook, we have two choices for where the where the carbocation forms. That could form here in the tertiary site, or it could form here in the secondary site. And we've learned that tertiary cations are more stable via hyperconjugation. So this is going to be the preferred cation intermediate that is formed here. Then we're going to draw the bromine. So when HBr loses the H, we then are left over with the bromide. And of course, the bromine is a good nucleophile and can attack the carbocation in a nucleophilic attack arrow push. This leads us directly to the products. However, we want to think about any possible stereochemistry that might be around in this product. So let's look at this cation. If I had a bromine here, well, I have four different groups attached to the cation, or attached to this carbon. So I'd have a propyl group, I've got a methyl group, I've got an ethyl group, and I'll have a bromine as the fourth group. And those are four different groups. So I need to draw my product with wedges and dashes indicating that it has a stereo center. To do that, I'm going to leave off the methyl, make that a wedge, make the bromine a dash. And so this is a stereo center. And because I've formed one stereo center, I need to make sure that I form the enantiomer of this molecule as well, the opposite stereo center. Because there was nothing in my reaction mixture that should prevent the formation of one of those enantiomers. If one of them forms, both will form. So I have a pair of enantiomers here. And we could have predicted that back at the beginning of the reaction, where we observed that this alkene is unsymmetrical. It has the potential to form a tertiary cation on this side, secondary on this side. So our bromine will add to the tertiary cation, and that will give us four different groups attached to that carbon: the bromine, the methyl, the propyl, and now this piece becomes an ethyl group after we add a hydrogen to this carbon. And so we can recognize that, yes, indeed, we will form two racemic products. We will form the R product and the S product in equal amounts. Let's look at the second example here. I have basically the same thing, except I've moved the alkene to the end of the carbon chain. So the first step, I'm going to protonate the alkene just like before. I'm going to draw a carbocation intermediate just like before. Here I'm going to draw the carbocation intermediate on the secondary carbon as opposed to the end carbon, which would be primary. This is the more stable intermediate. And then I will say, hey, this is a secondary cation. We could even write that right there if you want to. We can investigate this secondary cation for potential rearrangements. And as we saw on the previous question, there is a possibility of forming a tertiary cation here if the opportunity presents itself. So if I do a hydride shift, I could put a tertiary cation right here, and that's indeed what is going to happen in this case. So here's a rearrangement. Anytime you form a cation, a secondary cation I should say, you should be on the lookout for rearrangement possibilities. And now that I have this tertiary cation, I have a bromide that I can react it with, and I'm going to get the same two products that I drew on the top of the slide. I'm not going to redraw them here. This is the same cation. I'm reacting it with bromine. So these will be the major products. And I'm going to switch colors. Anytime that you form a cation and we have anions present in the reaction mixture, this cation could also potentially react. So I could draw another mechanism where the bromine reacts as a nucleophile with the secondary cation. And let me look at the bromine here. Is that a new stereocenter? Ask yourself that. Well, We've got a bromine, we've got the hydrogen that I didn't draw, we've got a methyl, we've got this 5-carbon piece of the molecule. So I would say, indeed, it is a stereocenter. So let's go ahead, make that into a wedge. Let's draw the other one. And I want to do one more thing. You'll notice that this is also a stereocenter. And just to be fully correct, I'm going to change that into a specific stereocenter and not a generic one that doesn't have any R or S stereochemistry. So that's going to be like that. This hydrogen is on a dash. However, once the rearrangement happens, now this is no longer a stereocenter. I don't need to worry about any wedges or dashes here, and certainly it will still go on to produce these two products. But if I take this secondary cation and react it before the rearrangement happens, I will maintain this wedge on the methyl right here and right here. So let me fix those as well. And the point I'm trying to make here is that we started with a stereocenter on our molecule, and the majority of the products will have destroyed that stereocenter and then recreated a new stereocenter in that place. But some of the products, with the green arrow push, created 2 new stereocenters just to the right of our original stereocenter. And so now you can see that these green products are not enantiomers. Like these, the blue products up here, enantiomers. And of course, these products are also enantiomers. Those ditto marks refer to what we have above. But the green products are not enantiomers. Can you tell me what the relationship of those two products are? And of course, they are diastereomers because they have 2 stereocenters. And as we compare the 2 molecules, one of them is the same configuration, that's this one, and this one is flipped. And so that's a good definition of diastereomers. Also, they are not mirror images, they are not superimposable, yet they have the same connectivity, so they are not constitutional isomers. They just differ in some of the 3-dimensional relationships of their bonds. That's this bond to bromine. So those are some considerations that we need to take into account when we do a hydrohalogenation. And more generically, anytime we form a cation, we need to take into account the possibility of rearrangement, as we saw with the blue arrow push here, and the fact that this higher energy cation will probably react a little bit to make minor products that have a less substituted halide. So let's call these minor. And I already identified those as the major products. Let's move on to one more example. Here we have an example with a ring, and we have again an alkene and HCl. And just like before, I'm going to modify this a little bit so that we see that there is a stereocenter here. So just like before, the alkene reacts in a proton transfer arrow push. We're forming a cation on that secondary position. And then we can observe that we've got a tertiary hydrogen here that could probably do a rearrangement. So I'm going to show that as my major product. That will create a planar carbocation. I've lost the stereochemical information that I had to start with. And then I'm going to react this with the chloride. Now the question is, am I creating a new stereocenter? If you look at this ring, I have a 5-membered ring. One half of the ring contains the pair of methyls, the other half does not. So I am going to create a new stereocenter. So I could draw this molecule, and then I could draw the enantiomer of this molecule. And I know I'm creating a pair of enantiomers because I had no stereochemistry to start with when I did the nucleophilic attack on the cation. And I've created just the one stereocenter. So I have a pair of enantiomers here. And that would be the major product. In this case, the minor product would be reaction of the chloride with the cation here. And that's also going to create a new stereocenter. So now I need to draw two stereocenters on my molecule right next to each other. And you can see, I'm going to erase this one after I draw it because I want to show you how this might get a little confusing if I decide to do this. So that looks a little strange because we've got the dash, the first dash coming, or first wedge coming out of the ring, and then we've got another wedge, coming out of what appears to be the first wedge. So let's erase that portion of the molecule and find a better way to indicate how we would draw this. I want to maintain the hydrogen going backwards, so I'm going to draw that right here. I want to put a wedge here for my chlorine and complete that with my methyl group. Now I could actually leave this alone. You and I and other organic chemists are perfectly capable of assigning the stereochemistry on this carbon even without having a wedge present. We know that the hydrogen's in the back. We can assign priority, count 1, 2, 3, come up with an R or S assignment. So I don't need a wedge here. I could put one in if I wanted to. I could put one in on the bottom portion of the ring. That would be perfectly acceptable. I could put one on the top portion of the ring if I wanted to. That would be also perfectly acceptable. I like the bottom portion better, so I'm going to put that right there. And if you don't believe me, let's go ahead and assign stereochemistry for this stereocenter. Actually, first, I'm going to draw my other diastereomer. So the stereocenter on the ring is unaffected by this reaction, adding the chlorine to the secondary cation. So I have these two, they are diastereomers, and they are certainly the minor product. By minor product, I mean they might form in 5 or 10%, whereas the major product is going to have 90 to 95% of this tertiary alkyl chloride. So let's go back to my red dotted carbon. Let's assign the stereochemistry on that carbon. So I think the carbon bearing the chlorine should be number 1. The carbon in the ring closer to the methyls should be number 2. The carbon on the other side of the ring should be number 3. If we count 1, 2, 3, that gives me a right-handed turn. That gives me R stereochemistry. This one's also R. Now let's go back to the same carbon on our carbocation starting material. Let's assign that stereocenter there. Actually, probably be easier to assign it here because the cation is going to confuse things when it comes to assigning priority. So let's look at the priorities. This alkene, thankfully, is still priority number 1. The side of the ring with the methyls is 2, and the other side of the ring is 3. 1, 2, 3, we have R here. And so you can see that it doesn't matter if the wedge is in the ring or if it's outside the ring, as long as I'm keeping the hydrogen in the back. And if I draw this hydrogen in blue here, that hydrogen is still in the back when I started. It's still in the back now on my intermediate here. And so it doesn't really matter where that wedge is as long as the hydrogen is in the back. The wedge could be on the outside of the ring or on either of the ring carbon-carbon bonds.